everyone. The pleasure to have Professor José Miguel Hernández-Lobato. He's a professor at the Department of Engineering, and he's formerly a postdoc at Harvard's Intelligent Probabilistic Systems Group, and also at the Department of Engineering. Today he's going to talk about free energy estimators with adaptive transport. What is really a FEAT is the acronym as well.
Great, thanks. Thanks for inviting me to give this talk here. And I will be talking about this work that was accepted recently at New Rips. And it was a joint work with these amazing collaborators. One of my PhD students, Jarzynski, and collaborators, Joanqui Du, Francisco Vargas, Joanqui Wang, Carla Gomez, and Eric van den Eigen. And I have to say that most of the work and the real contributors of what I'm going to talk about are Yao Yun and Joanqui. They deserve all the credit for this. So I'm going to start with some motivation for the problems that we want to solve. And we are interested in chemistry and in molecules, and to know what's going to happen with molecules in the real world, okay? We may have a new molecule that could be a new drug to treat a disease, and we have our example molecule here. And we might be interested in knowing if this molecule is going to be happy to be mixed in an environment with water molecules. And we are going to call this state A. The molecule is happy to be with water molecules, or it could be that the molecule doesn't really like to mix with the water molecules, and it's not going to get surrounded by them. And we are going to be in state B. We are going to be interested in computationally answering the question, what's going to happen in the real world? We are going to have a state A, or we are going to have a state B, okay? And the way to answer this question is to first have a model for the energy of the atom configurations in 3D space. This could be a model based on physics. I'm not going to care much about where this model comes from, but I assume that this is available. And this model is going to give us some energy function over the space of molecules. So this axis here is the possible space of configurations of molecules, and maybe in some of these regions of the space, the molecule is mixed with the water molecules. And there are interactions between the water molecules and the drug-like molecule. And we have a state B, and in a state B is just you have in vacuum water molecules together, you have in vacuum these molecules separated, and they don't talk to each other, they don't see each other, they are completely far away, okay? And there is going to be some configuration of the space that corresponds to state B, and there is going to be some energy for the configurations of the atoms in that space. From these energies, you can go to probabilities using the exponential function of minus the energy and adding a normalization constant. These are called the Boltzmann distributions. And if you have access to these energies of the configuration of molecules, you can obtain the probabilities that the molecules will be in some particular configuration. So from the energy function, you obtain now a probability density. And the question that we want to answer is, what's going to happen in the real world, state A or state B? The answer is, which state has more probability? What is the probability mass, the area, and the densities? These are unnormalized densities. They can be unnormalized densities. What is the area of these densities? Okay, unnormalized densities. The bigger one of the areas, the more likely that thing is going to happen in the real world, okay? And you're going to call the free energy difference the difference between the areas, the difference between the normalization constants of these densities, okay? And our goal here is going to be to estimate these free energy differences. These are super important quantities, especially in drug design. If you want to design a new drug, you want your new drug to mix with water, because otherwise it's not going to be assimilated by a person taking your drug, for example. So how do you calculate these free energy differences? It turns out there is a state-of-the-art method that allows you to calculate these free energy differences. Okay? You're going to have one distribution or one density, PA. This corresponds to a state A, and we have it here in red. And we have the other distribution. These are normalized distributions corresponding to state B, and it's shown here in red. And we want to estimate the relative difference in the areas of these distributions. So there is this state-of-the-art method called M-bar, which is very simple. And the idea is that you are going to create interpolating distributions between the two, which are shown here in these plots. Okay? And you're going to generate now samples from all these distributions. So you're going to generate samples, and even if your distributions are normalized, you're going to have maybe samples from this PA distribution, and then you have also samples from P2 distribution, and so on. You have samples from all these distributions. And N-bar is going to estimate the normalization constants of these distributions. It's going to give you the right height of or right scale for these curves. You're going to multiply the curves by a constant to normalize them, and you're going to get the right scale. And the way actually M-bar works is very intuitive from the machine learning point of view. If you have experience in M-bar is also used quite a lot in computational chemistry. And if you try to understand how M-bar works from the computational chemistry point of view, it's a nightmare. It's extremely difficult to understand what's going on. If you think about what's going on from the machine learning point of view, it's extremely easy. M-bar is solving a multi-class classification problem in a similar way as naive Bayes. Okay? You can think about generative classifiers in machine learning. In generative classifiers, you have access to the class probabilities. Okay? And you can estimate the probability of one data point coming from a class based on those class densities. You have the class densities. Think about naive Bayes with a mixture of two Gaussians. So here we have two distributions, PA and P2, and then we have samples, and then we could think of estimating a naive Bayes classifier that is trying to guess from which distribution each sample comes from. Is this sample here coming from distribution PA or from PB? Is this sample here coming from distribution PA or P2, sorry? So you try to learn from the samples from which distribution they came from. And the parameters that you're going to estimate are the normalization constants, the heights. So you just try to solve a classification problem. You do it by maximum likelihood. Your free parameters are the heights of the densities. Okay? And if you solve the maximum likelihood solution for that problem, that's the M-bar. Okay? The M-bar equations, there are some update equations here. They look very complicated. The way it works is that you initialize your log normalizers to some values. You plug them into this formula, and you update each log normalizer as a function of all the other log normalizers, and you repeat this several times. These are just maximum likelihood update equations for a classifier that tries to guess from each of these curves, from each of the samples from which curve it came from. Okay, that's the basic idea. And the cool thing is that M-bar has minimum variance, minimum asymptotic variance. So it's almost the best you could do. Okay? So that's great. This is a state-of-the-art method. I didn't tell you how you get the intermediate distributions. You could do it, for example, removing the interactions between the atoms in the drug-like molecule and the water molecules. There are ways to do this. But I mean, it's something that you can do easily. You generate samples with Markovsky and Monte Carlo. You run M-bar. You solve your problem. That's great. But you need to draw samples from the intermediate distributions. And maybe you don't have those samples from intermediate distributions. Or maybe it's expensive to generate those samples. Maybe evaluating the energies could be actually quite expensive. And you could imagine that you have now the two distributions for state A, for state B. You may have samples from those, but you don't have samples from intermediate distributions. In that case, M-bar is going to run into problems. And we are going to propose in this work an alternative based on generative modeling techniques that will be able to give you accurate estimates of the free energy using only samples from the one distribution and the other without having to access intermediate samples, okay? So you have samples from PA, you have samples from PB. I'm going to just to make it clear, I draw the samples here. You have samples from these distributions. And then how do you estimate the free energy difference, the differences between normalization constants? Very simple thing you could try, importance sampling. Very simple technique. You could try to do importance sampling here. And the free energy difference is shown here, is the minus the log of the ratio between normalization constants. Set 2 is just this integral here. Okay, and then you can multiply by P1, divide by P1, and then write it as an expectation with respect to P1. And then here you have now exponential of differences between energies. And in the end, it's just an expectation with respect to samples from P1 of these differences, of the exponential of the differences between the energies. That's important sampling. You could do this. People don't use this in practice. You don't use this in practice because it has high variance. And this is something well known in importance sampling. In high dimensions, if there is no significant overlap between these distributions, importance sampling will have high variance. You can reduce the variance of importance sampling using something called bar, which is the version of M-bar, but with only two distributions. You don't have intermediate distributions. And it's shown to have optimal asymptotic variance. It's better than importance sampling. And it's also a method that not many people in machine learning know about. But it allows you to estimate these differences in normalization constants with way less variance than importance sampling. It's similar to M-bar in the way that you start with a guess of the difference in normalization constants, this C, and then you update this update to get an estimate, again, an updated estimate of the free energy, and then you repeat the process, okay? So bar has way less variance than importance sampling. But if there is no overlap between the distributions, if there is no overlap between these two distributions, P and A and PB, it still suffers, and it will have high variance. Okay, so you're going to still run into problems into that. So what can you do instead? Another technique. This is more recently proposed based on generative modeling techniques. Do some transformation of the data such that there is high overlap between the samples. Okay? You have samples from your first state. You are going to do a transformation of those samples that maps them into a new distribution P1 prime that has high overlap with the target distribution for the second state. And the way to do this could be by doing continuous normalizing flows. Okay? Flow matching, a technique widely used now in generative modeling. You could use this. If you have data from P1 and P2, you can learn a mapping between the two, okay? And once you have this mapping, you can do importance sampling, okay? The problem is that to get the density of the transformed samples, you need the density of this P1, okay? To do importance sampling, for example, you need to solve this formula with normalizing flows, okay? There is this thing here. This is a divergence operator. And typically, this is the normalizing flow. It's going to be the output of a neural network that receives a data point, and it outputs a vector with the same dimension as a data point, and the divergence is the gradient of each of the outputs of your neural network with respect to the inputs. So if your data has dimension d, you need to backprop over your network d times to calculate just this divergence, and it appears in an integral. It's going to be extremely slow to calculate this. So this works only on very small problems. As long as you go to bigger problems, where you have maybe a large number of atoms, the dimension of the problem increases, this thing is expensive and you cannot apply it in practice. What I'm going to tell you today is about a technique based also on generative modeling methods that avoids having to calculate this divergence. And it's going to be more scalable, and it's going to allow us to give us accurate estimates of the free energy difference in bigger problems. Okay? And the idea is as follows. What we are going to do is, in similar to this target free energy perturbation, what we are going to do is do a mapping between the initial distribution and the final distribution. We are going to do a mapping, but we are going to do that mapping using stochastic differential equations. Okay? We are going to start with a sample from the first distribution PA, and then we are going to run a stochastic differential equation that is going to transform that. We start at time 0, okay? So we have time 0 here. And then we end up with a sample at time 1 that follows the second distribution, okay? I'm going to use these stochastic differential equations. I didn't tell you how I get them. I'll tell you later how to get them. But we're going to have here a Brownian motion in a forward direction. We are going to have some function here. This is the gradient of the energy of the marginal distribution of the samples of the SDE. I'll tell you later how we get this. And this is another function that is going to be a control term that ensures that we have the right marginals, that it has this energy. It has this funny form, this SDE. There is a well-reasoned way why it has this form. If you are curious, I can tell you about it. I mean, this is very similar to Langevin dynamics. No? If you follow Langevin dynamics, this would be the score of your target, and then you have like some Brownian motion here. But the problem is that your target here depends on the time t. And Langevin dynamics doesn't work if your target changes as a function of t. Okay, that's why you need the control here to guarantee that you sample from the right distribution. Anyway, we have these SDEs. They are going to map between the two distributions, and the interesting thing is that they are going to allow us to calculate the free energy difference without having to use this divergence, integral of the divergence, that we had to do with the normalizing flows. We don't want to do this, okay? And the SDEs allows us to do that. We have a forward SDE that starts with samples from PA and ends up in samples from PB, and we have a backward SDE that starts on samples from PB and ends up on samples from PA, okay? And this shows an example of how this would look like. You may have like an initial distribution here for PA. You have another distribution here for PB, and you have the SDEs showing here some trajectories that interpolate between the two, okay? And there is obviously some intermediate samples from when you go. This would be time 0. This would be time 1, okay? And the key thing is that if we have this SDE that map between the two distributions, we can now calculate the free energy difference doing important sampling. But now we don't do important sampling between PA and PB. We do important sampling between the SDE trajectories, okay? The probability distributions of the SDE trajectories. And they are going to be overlap. We are going to have guaranteed overlap between them, okay? By the way we construct these SDEs. So what we are going to do is now discretize the SDEs. This shows equations for a discretization of the SDEs. is the same functions that we had before, the gradient of the energy, the control term, and now here we're going to have some Gaussian noise. And we can do important sampling. We can do important sampling with samples from the forward SDE. This would be X0 forward, or with respect to samples from the backward SDE, X1 backward. And we are going to have less variance because there is going to be now overlap between these SDEs. And that's the key thing here. You can do now important sampling over SDE trajectories and not between the distributions. There is no overlap between the two distributions, PA and PB, but there is overlap between the forward SDE and the backward SDE. Okay? And we can do even better. We can do something better instead of important sampling. We know that bar, something similar to M bar, but with only two distributions, has minimum variance. So let's do that, but with the SDE trajectories. So you can do now a minimum variance method that is going to estimate the normalization constants between the SDE trajectories. Okay? Just to clarify, the SDE trajectories, the probabilities that you obtain for one is you have here the normalized distribution for PA, and then here you have the Gaussian transition probabilities that brings you from A to B. And for the backward SDE is the other way. You have here the probability of PB and normalized, and then you have here the Gaussian transition probabilities that bring you from PB into PA. Okay? And you can show that the expectation of this is going to be the free energy difference. Great. So this is the method. And the key thing is, how do you get your SDE models? Using the framework of stochastic interpolants. This has been a very successful framework. It has been proposed recently. It generalizes flow matching, diffusion, and the idea is that you are going to create now samples from the intermediate distributions of your SDs. Okay? You have samples from PA, you have samples from PB, and you're going to create intermediate samples from the SDE trajectories just by doing a combination of those. So you have these coefficients, alpha t and beta t. Alpha 0 is 1, so that at time 0 we are at PA, and beta 0 is 0 to guarantee that, and then alpha 1 is 0, and beta 1 is 1 to guarantee that at time 1 we sample from PB. Okay? We also add a little bit of Gaussian noise. This Gaussian noise is going to vanish at the boundaries, but it's going to be useful to estimate the gradient of the energy. The gradient of the energy is the score, and you can estimate that with score matching. Okay? The same as what you do in diffusion all the time, you can do it here as well. You can add Gaussian noise to your data, you can estimate, you can try to predict these epsilons. Here you create an interpolant, xt, you corrupt it a bit with Gaussian noise, and then you try to predict this interpolant from the sample that you generated, xt, and the expectation of that is going to be this score, this gradient of the energy. So you can estimate this with a neural network now by trying to predict the epsilons that you use to corrupt your data with Gaussian noise. And the control variable is just the gradient of the interpolant as a function of time. Okay? You can show that this happens as well. So you can now train two networks, one that is going to give you the gradient of the energy, and the other one that is going to give you the control term for your SDs. And you just need to train this from data from the distribution A and the distribution B. You don't need intermediate distributions, and you don't need to generate samples from the intermediate distributions. So that's it. You estimate your models, and then once you have your SDE models, you can estimate the free energy difference using the methods that I described. We tested this on some problems. The first one is a toy problem with mixtures of Gaussians, 16-mode mixture of Gaussians, 14-mode mixture of Gaussians. These are the two states. These are two distributions. Both are normalized, so the free energy difference is 0 because the normalization constant of both distributions is 1. The log of the ratio of 1 and 1 is 0. We also tested on a Leonard-Jones system. This is a synthetic system of particles that interact according to some potential energy. And we are going to calculate the free energy difference between the particles affected by this potential and the particles without the potential. And then we tested also on a molecule that is called an anine dipeptide. It's a simple amino acid. And we are going to calculate free energy differences between this molecule in vacuum and in some implicit solvent or in two states. This is a molecule and it can vibrate and the atoms can move. And we are going to consider the angles of some of the connections between the atoms. And we are going to say when this atom phi is in this range and this range, this is going to be one of these states. Okay? And when it's between 0 and 2, is one of the states, and the other state is otherwise. Okay? So this would be the other state. So we kind of partition the space of configurations of the molecules into regions, and we want to calculate the different probabilities for these states. How does this work in practice? We compare with M-bar. M-bar is a state-of-the-art method. You need to generate samples from the intermediate distributions, but it gives you very accurate estimates of the free energy difference. In the Gaussian mixture model, we know the ground truth, which is 0. And we see how our method does here and compare with the target free energy perturbation. This is using some flow matching technique. It requires to calculate this integral of the divergence. And we compare with another technique called neural thermodynamic integration that it's a baseline I won't describe here in detail. And here we see our method. It gives values that are close to 0, and actually closer to 0 than the baselines in this problem. Okay? In the Leonard-Jones problem, we have the values given by M-bar for different number of particles, 55 particles, 79 particles, and 128 particles. Target free energy perturbation doesn't scale to this size of problems, so we couldn't calculate the results of that method. You need to integrate the divergence. That method is not scalable. But our method here gives values that are actually quite close to the ones given by M-bar here. Okay? And then we have also results for an anine dipeptide, where we get values that are also similar to the reference. So we have here the reference, and here we have what we obtain with our method. So we get quite accurate estimates of the free energy difference using this technique. And we can see the importance or why you should use minimum variance estimators. You could just do importance sampling, or you could use the minimum variance estimator bar over the SDD trajectories. And you can see that the minimum variance estimator in blue converges very quickly here, converges very quickly to the ground truth or values very close to the ground truth value. But if you do importance sampling, you have high variance, and your estimator takes way longer to converge. Okay? So that's important to use bar. I think this is something that people in machine learning don't know much about, this bar method. It's quite useful. So just to conclude, some take-home messages. I have presented here this method FEAT, free energy estimators with adaptive transport. It calculates the free energy difference using only samples from state A and state B. We don't use intermediate distributions, and we don't need to sample from intermediate distributions. We use the framework of stochastic interpolants to learn SDEs that are going to map between the two distributions. And these SDEs will allow us to calculate the free energy differences without expensive things like calculating this integral of the divergence. We have proposed to use this bar-like minimum variance estimator that helps a lot. And we outperform existing baselines like neural thermodynamic integration and neural target free energy perturbation. This method looks promising, it's very interesting, but obviously it has limitations. Okay? What are the limitations? You need to train neural networks to characterize your SDs. Okay? You need first the data from distribution A and B, and then you need to train from this data your neural networks. And your neural networks in large systems may not be that accurate. they may make mistakes also. And then in that case, there is not going to be that much overlap between the SDE trajectories. The forward and backward SDE trajectories, maybe there is not such overlap. If you work in very high dimensional systems and your neural networks are not accurate enough, and then your estimates of the free energies can be inaccurate. Ideally, what you would like is to amortize the training of those networks. You could have problems where you need to calculate free energy differences. Instead of generating samples all the time with M-bar for those systems, maybe you could train neural networks that learn SDEs that map between the distributions and they generalize to new systems. And then in that case, you avoid training the neural networks. This is something that we didn't do, but it's something that could be some forward steps in this direction. So that's all I wanted to say. Thanks everyone for your attention, and I'm happy to answer any questions that you may have. Thank you.
Questions for Jose? Sorry, I should say Miguel.
Miguel, yeah, it's fine.
Well, there'll be plenty of time for discussions over coffee right after which we'll have one talk. But can I ask you one question?
Yeah.
So I read in your paper that you have applied this formalism to many different scenarios. And one of the things that piqued my interest was the phi-4 quantum field theory.
Okay, yes.
Can you tell us a little bit about the applications?
I mean, these applications. Yeah, it's an area that is a bit out of my expertise. This was done more by my collaborators that obviously have domain expertise in that area. So I'm not an expert in this quantum system. But I have to say, many of these problems, I mean, these results are very promising, and we can see how the generative modeling approach is moving forward and making more progress. These problems that I have shown here, and the problems where many people are working on applying generative modeling to molecules and all that, are still very toy, okay? They are very different from real-world problems. I think we are making steps towards solving things that are more and more realistic, but we are still far away from being able to solve real-world problems. Like a real-world problem where you might be interested in may involve simulating this drug-like molecule with water molecules, but maybe you need 500 water molecules, okay? And then with 500 water molecules, you have 3 atoms per water molecule, 3 coordinates per atom, then the dimensionality scales quite a lot. You go to dimensions of tens of thousands, hundreds of thousands, and then you will need models that are scalable and models that are accurate in those dimensions, and that can be quite challenging. We are moving into making these models more applicable, but we are still far away from the real-world problems where they will make like a big difference.
So what are the theoretical challenges to making this applicable for infinite dimensional spaces?
For what?
For making this applicable to infinite dimensional spaces.
Infinite spaces?
Yes.
We actually have a paper. I have a paper with a student where we extend the framework of stochastic interpolants to infinite dimensions.
Okay.
And you work with stochastic processes there. And we submitted this to a conference, and it's under review. But hopefully, I don't know, we'll see how it goes. It will be available if it is accepted very soon. But yeah, you could think about working in infinite dimensions. Yeah.
That's very impressive. Thank you. Any more questions? If not, let's thank Miguel again.
Good, thank you.
We have a coffee break now, and we'll be back in 15 minutes for the last talk.
Good, thank you for the invitation.